1. Same as saying that I have omega and I'm integrating expectation of x times the expectation of the indicator function of a, right? This is same as the expectation of x multiplied by the indicator function of a. And this is same as expectation of x times expectation of indicator function of a. Okay? Yeah, so that's a number, so you can pull it out. So you're going to get this. And now, this is same as expectation of x times indicator function of a, because x and independent, a are independent of each other. But this is same as this guy integrating over a x factor bb. But by definition, this is same as integrating over a the conditional expectation. That's it. So we started from here. So I took an arbitrary set from G and I integrated expectation of x over dB, and I show that this is same as integrating the conditional expectation of x given G over the same set A with respect to dB. So you can get rid of the integral, and hence you can get the equality.
But I have one confusion. E of x given G is an operator, right? It's a random variable. However, E of x is a number.
What do you mean by that?
Number 4 property. E of x given G is a random variable. E of x is a number.
No, it's okay. Whatever it is, okay. So your point is that how you are pulling out.
No, sir. How they are equal, I'm not getting the definition of their equality. Because that one is a random.
So what does this mean? That this conditional expectation is a constant?
Constant function.
Just always map to the same. That's what it means.
But sir, with respect to random variable अगर treat करें तो variable हो सकता है. अगर random variable x इसकी input treat करें हम.
But if you fix x, then that's a number.
But only that's
like since this is a random variable, so map. So what does this mean? That on the most of the omegas, this is a fixed number expectation of x, but not intervals. Are we happy with this argument? Neat argument. Then the 4 part, about the 5th part. What do you say? Tower property. Which like is the tower? The tower property. Of this. So by definition, we know something. In that you, for any b from G, you have this equal conditional expectation of x given G over this set B and its integral with respect to the property measure is same as integrating x with respect to this is what the case. So this is all the and since H is also part of G, so this is also true for any B in H as well. So okay, so for any B in H that is part of, okay, so any B
In H.
so here's the thing. And similarly for B in H, okay,
B या कोई और सेट से
B in H. Wait. Let's take A and H, doesn't matter.
सही
Okay, but B is an arbitrary thing.
सही
Since we have written things in the let's take A and H. Similar thing also holds for conditional expectation given H actually. So in other words, integrating A over conditional expectation of X given G, X given H
the same as
is
expectation
same
of X
as X
over A
over A this is yeah.
सही
So, like, these two holds.
ठीक सर
Now I would like to use the fact that H is a part of it.
so A must be part of
Okay,
not necessary
as well. Okay. Can I use the same symbol for both because these are arbitrary? So can I say that if this is the case, then the conditional expectation for any B, so for B in H, conditional expectation of any B X given H is the same as conditional expectation of X given G. Okay? Why this should be the case? So take a B from, okay, so take a B from H, this must be true. But the same B is in G, so this must be true.
सही
But these two are equal.
सही
These two should be equal as well.
ठीक
Okay.
सही
Now if you apply what? On this side, if I apply the definition of being conditional expectation, so in other words, is treat this as a random variable, as a quantity,
Property
call it
2
y
for
or
H.
something like that.
property 2 for H
Okay. Use the property 2 for H. So if you use the property 2 for H, treat this as a random variable. So this is same as compute the conditional expectation of the random variable X given G given H. ठीक है? We are done with it. But as a student, once you are presenting proof, try to put as much as detail. This is to just making sure that you understand it. Obviously, there are stuff actually at the back end. Like giving focus of argumentation is important. What I want to show next is that if X is non-negative, then the conditional expectation is also wrong. And I show it, define a set of for n in n. Let's take a n. That shows that the conditional expectation of X given G is less than minus 1. So in other words, it's the collection of the omegas for which the conditional expectation can be negative. So I'll combine all such ANs and I'll show that their probability is zero. That's what I feel my intention. Here's the thing. Then AN belongs to G. Question is why? Remember, these are measurable sets. Why they are measurable?
G measurable short number.
So because E of
Measurable G
measurable,
measurable
G
function.
Yes. Expectation of X given G is
G measurable.
basically G measurable. So in other words, I can treat this as the expectation of X given G inverse of the interval minus infinity
Minus 1
like that.
Right.
Okay. So since this guy is G measurable, so G measurable as well. So otherwise, this is important that we should keep track of things that we have.
Say
Now, if X is non-negative, then consider this. Obviously, the integral over kn of X with respect to dp must be non-negative. Alaji, if X is non-negative, take any set, integrated must be non-negative. But this guy is same as the conditional expectation of X given G, Gp over an. Okay?
say
But I can say that, okay, this is same as, because on an,
yes.
conditional expectation is less than or equal to
Same,
minus 1
same.
over n, so this must be less than or equal to minus probability of an over
And
n.
right.
This must be. If this is the case, take n goes to 0. Okay. So they imply that probability of an must be 0. Now to summarize all this, what I have to show, let's combine all these.
Sir,
And let's consider.
n goes to infinity से ये
Sorry.
n goes to infinity पे क्या है ये p of a and g.
Like that. What if I take, you know, okay. What if I take
So n is a positive number,
n is a positive number,
and this is
probability is a positive number, n is a positive number,
So-
and this inequality can only hold when p of n is zero.
Ah,
There is nothing.
same.
There is no other possibility. There is no other. Otherwise, if you take this as this is positive, both are positive whether you like it or not.
Say
So you can only achieve equality if this is zero.
say
And now I'm saying let's consider the probability of the conditional expectation X is given G being a negative. Then this is same as basically, because no matter what negative number it is, you can always find a natural number such that this is true. So in other words, I can say that this is same as the union of n equal to 0 to infinity a. The probability of the union of a equal to 0 a. Okay?
method.
So let's get rid of the probability. Consider only this set.
Say sir.
Union of I equal to 1 to infinity a and n equals 1 to infinity a. If this is true, all these are here for sure.
सही है
Take an omega from the union, it must be in some an. So for that an, this condition is.
सही
Okay? Now take an omega that is a negative number. So
Same.
for which the conditional expectation is negative.
सही है फिर
You
वो
can always
माइनस
find a natural number. Okay.
सही
So in other words, this number is, so this omega is going to fall into one of the an side. So you can prove this equality only. So what you need to do is then now take the probability of these both sides. What would be the probability of happening this?
Less than or equal to.
So this is less than or equal to sum of I equal to 1 to infinity, the probability of
Yeah.
ans. That's at 0, so this must be 0. As we're gonna say, happening of this is so for the omegas for which this is true has a measure of 0. Hence, the opposite is true. In other words, the conditional expectation. In other words, for most of the omegas, conditional expectation would be sure. That's the case. So let's end here.